Hi everyone, welcome. Today I'm going to be going over one of these tools that's really helpful to us in a lot of math courses, and that tool is partial fraction decomposition. If you are not familiar with what partial fraction decomposition is, it's essentially this idea that lets us take a more complicated fraction, specifically a rational function. So that's one that has variables in the numerator and variables in the denominator, something like x squared plus x, and it lets us go from this single fraction with variables in the numerator and denominator to multiple fractions, something that would look like 2x plus 1 minus 1 over x. This process of going from one large fraction to two or more smaller fractions is that process of decomposition, and the reason why we talk about this, or why I'm going over this today, is it's really helpful to us in a lot of different classes. In those pre-algebra classes, they specifically just want you to understand how to go from here to here, since so frequently we are talking about going the opposite direction. But when we're talking about later classes, getting to this point makes things a heck of a lot easier, because if I try and do the integral of this, that's a lot more difficult than trying to do the integral of these two functions separately. So that's really why knowing how to do partial fraction decomposition is so important to us. Besides that, there's just some things that we need to know. The big important thing when I'm talking about partial fraction decomposition is understanding how to factor, because it's going to be very difficult for us to go ahead and do this partial fraction decomposition if the denominator of my larger, more complicated fraction is not simplified. So definitely whenever we're talking about this, we need to factor. So in this case, my factor denominator is going to be x times x plus 1, and we can see that here. The reason why we do that is it's going to affect what is essentially going on here. So now, just running through this one real quick, in order to go ahead and set up these problems, essentially what I'm going to do is take each of these. I would do, in order to keep things similar, we have x plus 1, and then we have x. This obviously up here is our simplified case, what we would get to after. But the real question is, how do we get there, right? You may have seen this before, but as a reminder, what we would do is we're essentially filling in undefined coefficients so that we can go ahead and solve for things. I like to set this up as an equality. Sometimes I go ahead and skip steps because you get used to seeing things like this a lot of times. But using this equality is very helpful for us because it reminds us of some of the things that we can go ahead and do with fractions. Like in this case, fractions are technically division. So what I can go ahead and do is x times x plus 1. And then the only other important thing is make sure you're remembering to take that denominator and multiplying it to the whole right side of this equation. That lets us go away, and then we get this x minus 1 is equal to a over x plus 1 times x plus 1. The x plus 1s are going to cancel, and in the second case, I'm also being multiplied to x and x plus 1, but the x's are going to cancel. And then I have a x plus b x plus 1. Now this is enough information for us to really go ahead and solve. But before we go ahead and get into solving it, there are some other things that we should note. The numerator of any of these fractions is going to have a power of 1 less than the denominator. In that case, right, this is an x to the power 1, and this is really ax to the power 0, with the idea that any number to the power 0 is going to be 1, and it would just leave us with our constant. The important thing to remember about that is, let's say I have a fraction with like some x squared plus 1. multiplied to x, and there's something going on in the numerator. Well, I can still go ahead and set it up as two separate fractions on the other side of this equality. This one, because it's an x to the power 1, is just going to end up as a, or, you know, any variable. Since I'm starting here, I start with a, just going in alphabetical order, plus things can get moved around a little bit. But in this case, because I have an x squared, I'm going to at least need to test to see if there needs to be an x in the numerator. And the way I would do that is by doing bx. But that's not enough. Whenever I do it, I also need to do, I really should have said c instead of d, but I'm always going to add that. And so then if I have some x cubed term, the thing in the numerator is going to be ax squared plus bx plus c. And the pattern goes on, and you can simplify it such forth forever. Okay, and that's that general idea here. So now we're looking here. I'm going to go ahead and clear this and then rewrite this guy right here. So I have x, let's make sure I have it written down correctly, x minus 1 is equal to ax plus b times x plus 1. Okay, now we have numerous ways that we can go ahead and solve these. This is a really good case of when we can use that substitution method, where that substitution method says, I can plug in any value for x and solve for the variables. This is a good case for the substitution method because if I plug in certain values for x on this right-hand side, it's going to cause the term that it's in to go away. For example, if I set x equal to 0, and then we look at what happens when it plugs in, I have 1 minus 0 is equal to a times 0 plus b times 0 plus 1. Well, this is going to go away because any number multiplied with 0 is, of course, 0. And then I have this negative 1, b times 1 is just b. Obviously, that makes sense. And it also follows what we had previously found. Similarly, I can now change this function and still go ahead and solve for a. In this case, when I do that second step, I think it's going to be easiest to plug in x, or equals negative 1. And when we observe what's going to happen, we get negative 1 minus 1 is equal to a times negative 1 minus negative 1 plus 1. Observe that here this goes to 0, so there's nothing here. So I get negative 2 is equal to negative a, and therefore 2 is equal to a. Again, that would provide us that when I plug things back in, i.e. I get back to this x minus 1, x squared plus x is equal to 2 x plus 1 minus 1 over x. The only thing I would recommend is making sure to identify which of these fractions over here has which variable and make it very clear for yourself because that's going to make things a little bit easier to identify. Besides that, we ended up with the same answer. Substitution is really great if you have unique denominators. In this case, my denominators are only x plus 1 and x. However, let's consider a case where I have repeated denominators. So this one, let us go with, let's just keep things simple, with x plus 1 squared in the denominator and then an x. And then let's go with like 2x plus 3. This one might turn out a little bit crazy, but when I go ahead and set this one up, this is another important generalized rule when I'm talking about partial fraction decomposition, is I need to keep in mind that this is x plus 1 squared. So this is going to end up with two fractions. The first fraction is just going to be x plus 1, and then the second fraction is going to be x plus 1 squared. Super fun. The thing to observe here is this would continue for every case. So let's say I had an x cubed, and it's just x cubed, not x cubed in some other term like x cubed plus 1. This is just x cubed being multiplied to something else. So when I would do this and do my partial fraction decomp, I'm going to have one fraction just left right here in that denominator, something right here, plus, and then because it's cubed, it's going to get 3 fractions to itself. One is going to be x, one is going to be x squared, and the third is going to be x cubed. And whenever I do partial fraction decomp, it's always going to follow this pattern. So that can go away. Now the thing to observe in this case is I also have an additional term, which is that additional x. Nice things are the a, b, or c, or like ax plus c, all of that is only determined by the power on x, not the power of the denominator, right? Because technically, this whole thing is squared, but because this one is just an a, this one is just going to be a b, and this is just going to be a c. It's going to follow that same pattern that we've already talked about. So now I'm going to do that same process where I'm going to multiply that denominator onto both sides, and it's going to get multiplied to this whole thing. Okay, so that leaves me with just this 2x plus 3 on the left-hand side. And to skip through into looking at what's going on, when I multiply x plus 1 squared to x times x to this first term, I'm going to get a x plus 1 times x. This second one is just going to be left with 0, and this third one is going to get left with x plus 1 squared. So let's first look at that substitution. This is still a great one that we can do the substitution in. It just is going to take an extra step for us, because when I go ahead and plug in x equals 0, just like before, I'm going to get 2 times 0 plus 3 is equal to a times 0 plus 1 times 0 plus b times 0 plus c times 0 plus 1 squared. And so anything with a 0 is going to go away, so I'm just left with c is equal to 3. Then I'm going to do the same thing with the -1. I would probably, when doing these problems, make an intermediate step changing this function, but to make things a little bit quicker for us, I'm going to replace this with 3 right there. So now I'm going to plug in -1, and when I do that, I get 2 times -1 plus 3 is equal to a -1 plus 1 times -1 plus b times -1 plus c times -1 plus 1 squared. -1 plus 1 is 0, so this is going to go away and this is going to go away. So I'm left with -2 plus 3 is equal to -b, or 1 is equal to -b, or -1 is equal to b. So then I can go ahead and replace this value. So erasing this. This is a case where substitution is still fine. The thing to observe here, though, is I've gotten rid of all of the obvious routes of substitution. I can still go ahead and substitute, that's always true. Specifically, I'm going to replace these since I've now identified them. So this is -1 and this is 3. But since I've used up all of my obvious substitutions, I just need to pick a third value. In this case, I'm going to go ahead with 1. If you didn't have a case of 0, 0 is also super great, but you're just going to have to pick a third value and solve for a. So when I do that, I end up with 2 times 1 plus 3 is equal to a times 1 plus 1 times 1 plus -1 times 1 plus 3 times 1 plus 1 squared. So then on the left-hand side, I'm left with 5. I get a times 2 times 1, so that's going to be 2a. Then I have this -1. Then here I get 2 squared, which is 4, times 3, which is 12. So then that's plus 11, and I'm added over. So 5 is equal to 2a plus 11. Subtract it over, which is going to be -6 is equal to 2a, which is then going to imply -3 is equal to a. So still obviously good for substitution. This case is still really good for us because I don't have those things like an x squared plus 1, which is not factorable, that I then have to deal with. It's still super good for us. So substitution is generally the first route that I take, but it's not the only route that we have to take. So let's consider the case that I now have 2x minus 3 over x times x squared plus 1. I like this one. This is a good case of something that's not just x in the denominator. So when I go ahead and set this up, my denominators are going to be x and x squared plus 1. Again, this one, because it's just an x to the first in the denominator, is going to get an a, and this one is going to get bx plus c. Just like before, I'm going to go ahead and multiply the denominator onto both sides. And the way I'm going to set this one up is like this. So this one is going to become a times x squared plus 1, and then this is going to become bx plus c times x. Please note that I'm putting bx plus c in parentheses, and that's appropriate. I would say whenever you're in doubt, add in the parentheses, because if you don't, it's going to seem like that x is only being multiplied to the c, and that's not true. Because when I would multiply this x times x squared plus 1, it's getting multiplied to this whole fraction, so it essentially looks like this. And yes, this goes away, but this thing is still being multiplied to the whole fraction, which we can interpret as having its own set of parentheses. My next favorite way is to essentially deal with this as a system of equations. The thing to note about trying to deal with this as a system of equations is it's going to be easiest if you multiply things out. And by that, I mean I have 2x minus 3 on the left-hand side of this, but I want to expand. So on the right-hand side, I end up with ax squared plus a. There's a plus sign in between. I just dropped it accidentally. And then I have bx squared plus cx. And then I get to here. Then I can also interpret this left-hand side as having a 0x squared. One of the ways that we can go ahead and set this up as a system of equations is essentially say all of the x squareds on the left-hand side have to add up to the x squareds on the right-hand side, or vice versa. All the x squareds on the right-hand side have to be equivalent to the x squareds on the left-hand side. So I can break this up into essentially 3 functions, where I have 0x squared is equal to ax squared plus bx squared. And then I can have my x's, which is 2x is equal to cx. And then I have that third one, which is -3 is equal to a. This is the equation for all the x squareds, then all the x's, then the things, the coefficients or the constants. Then I can go ahead and get rid of my variables, my x variables specifically. So then I'm looking at 0 is equal to a plus b, 2 is equal to c, and -3 is equal to a. Well, right off the bat, this is really nice because it identifies 2 variables for us right away that I can go ahead and plug in. So then I'm left with -3 and a +2, and then I just have to solve for b, which I can do since I've identified a by plugging in here. So 0 is equal to -3 plus b, and then therefore 3 is equal to b. Whenever I'm doing this as a system of equations, this is my favorite way to go about doing that, but it's not the only way that you have to. If you're familiar with linear algebra, you can always set it up like that as well, where you technically would have, like in this case, I could set it up as a matrix. I'm going to go ahead and erase this real quick right here. You could consider these 3 functions as essentially being 1a plus 1b plus 0c is equal to 0. 0a plus 0b plus 1c is equal to 2. Just note that these are being multiplied. And then with that last one, 1a plus 0b plus 0c is equal to -3. And so then you could set this up as a matrix that looks like, I like to put this line down the middle because to me it visually represents like an equal sign. And then if you went ahead and row reduced this thing like normal, you should end up with something that you should end up with the same solution that we found for A, B, and C. It's another option. Definitely if you are doing partial fraction decomposition, computer algebra sources or linear algebra calculators are going to be super helpful to us. This is just ways that we can go ahead and do this by hand. Okay, so our last method for doing partial fraction decomposition is through derivatives. Let us look at this more simple one. Again, we can always look at these with more complicated ones. They just take a lot more time. When I'm looking at this, I also want to go ahead and factor out this denominator first, which based on it being a difference of squares, I know it's going to be x plus 1 and x minus 1. And then because it's an x at first, it's just going to be a and b. Then when I go ahead and multiply x plus 1, technically an x minus 1, to both sides, I end up with just 6 on the left-hand side, and a times x minus 1 plus b times x plus 1. With this derivative method, I'm going to go ahead and factor out or expand. So I end up with ax minus a plus bx plus b. Then we're going to go ahead and take the derivative in terms of whatever our variable is. Our variable here is x, so I'm going to take the derivative on both sides, which might seem a little bit weird, but we can always consider that both sides are technically equal to f of x, and then I'm just setting them equal to each other so that they're equivalent. When I do that, I end up with a 0 over here is equal to a plus b. Or I can say that a is equal to negative b. There are going to be cases when you do this derivative method that you will end up solving for an exact value, but there are also going to be cases where you can't. And this is a perfect example of when you can't. Instead, what I can do is go ahead and take a and plug it in for negative b, or vice versa. And so when I do that, and then I plug it in, then I have 6 is equal to, let's put negative b in for a. So then I get negative bx plus b, because this is a negative a, plus bx plus b. Obviously, my negative bx and my positive bx will cancel. So then I get 6 is equal to 2b. Divide over, so b is equal to positive 3, and then plug this in here. Therefore, a has to be equal to negative 3, and that's a good way that we can see about using that derivative. In any case, you can use any of these methods, that substitution method, that system of equations method, and its two variants, and that derivative method. I would recommend looking at some more difficult examples and getting familiar with whatever methods you feel comfortable with. And this really is just a practice thing. So I hope that was helpful, and good luck, everyone.